Kia ora Year 12 and 13. In this video, I'm going to show you how to use de Moivre's theorem to find complex roots. We're going to look at two examples, the two that I've got here. So find the fifth roots of 243 and then find the sixth roots of 1 plus root 3i. So if you're watching this and you're in my class, you should see straight away that this is going to involve special triangles. This one is a slightly easier one to start us off. Now, this isn't done very well at all in the A-level book because it's not part of the A-level syllabus. It is really, really important for level 3 complex numbers. So we're going to work out of the Ancient Delta book, chapter 18.3, page 236. So there are a bunch of really tough examples at the end of that section that I recommend if you're looking for some extension work. But the first thing we're going to do is just set up this first equation and see what's going on. So we're trying to find the fifth roots of 243. So we can write an equation that says z to the power of 5 is equal to 243. And if we wanted, we could rewrite that and say, well, that's a polynomial, and we can write it like this, and we're looking for where it's equal to 0. We know from earlier this year that the fundamental theorem of algebra tells me that there are going to be 5 solutions to that equation. Until now, we've been quite happy to say that the fifth root of 243 is equal to 3, right? So that's when we're working with the real numbers. But we now know that there must be out there somewhere in the complex number world 5 roots. It turns out that they are all going to be located symmetrically, and 3 is kind of like our anchor root. So I'll show you this picture nicely when we get through the question. But the answer here is going to have 3 drawn here, and then it's going to have the next 4 spaced evenly around here like this. But we need to do a little bit of work to get there. So when you're solving problems like this, you're always going to be working in polar form. Okay, so if you're starting off in rectangular form, as we are in the second question, the first step will be to convert everything over to polar, because de Moivre's theorem will make everything much, much better. So let's just start out by saying, well, what's z? We've got z to the power of 5 is equal to 243. So let z equal r cis theta. Now notice, guys, this is not exactly how the book does it, but this avoids us trying to apply de Moivre's theorem to fractional powers. So we haven't shown that it holds for fractional powers. We've shown that de Moivre's theorem works for integers, right? So in class we proved it for positive integers, but it does hold for negative ones as well. So if you do this presentation of it, you never have to say things that are a bit hand wavy, and it works out really nicely. So z to the power of 5 is r cis theta to the power of 5, and that equals 243. Now if we're writing 243 as a complex number, it's lying out here. So there's 243 there. So it's 243 cis 0 degrees. But it would also be true that 243 can be written as, so it can be written as 243 cis 0, but it can also be written as 243 cis 2 pi, right? I can spin that angle around, oops, that wasn't meant to happen, by 2 pi or 360 degrees. Right, so I call this the spin around thing. So that's one rotation of 2 pi. It's also true that 243 is equal to cis of 4 pi. So we can spin it again. So when we set ourselves up to solve one of these problems, the way that we're going to generate the extra roots is by acknowledging that it's not really 0 degrees. It's 0 plus any multiple of 2 pi. And that n is going to be an integer. So applying de Moivre's theorem now gives me r to the power of 5 cis 5 theta is equal to 243 cis of 0. Now I've mixed my degrees and my radians here, so let's work. We're working in radians today. So 0 plus 2n pi. And now we just have to match things up. R to the power of 5 is equal to 243, so r is equal to 3. 5 theta must equal 0 plus 2n pi. Theta is equal to all of this divided by 5. So 0 plus 2 pi on 5 times n. What we need to do now is to substitute in 5 different values of n, and out will pop z1, z2, down to the 5th root. And after that, they'll start to repeat. Okay, so let's just work systematically here. We start with n equals 0, and we'll have zn, so z0 is going to be just my real one, so my 3. So z0 will be 3 cis 0. When n equals 1, we get z1 is equal to 3 cis 2 pi on 5. I'm going to show you what these look like at the end. N equals 2, so just thinking about where we're working, we've got 3, 2 pi on 5. Now we're going to have 3 cis of 4 pi on 5. That's a 4 there, so around here. Now, we could keep going and put in 3, and then we'll get 6 pi on 5. But you know, I kind of have this thing about making my angle be between 0 and pi, or 0 and negative pi. So I'm going to move backwards and go to n equals -1 and start doing the ones down here. So z3 will be 3 cis -2 pi on 5. So I'm getting that by substituting n equals -1 in here. And the last one, n equals -2, gives me z4 is equal to 3 cis of -4 pi on 5. So there you go. We've got our 5 roots, which makes us feel happy because of the fundamental theorem of algebra. Just one thing on numbering. You can do from z0 up to z4. I usually don't do that, actually. I usually go z1, z2, z3, z4, and z5, right? It's just that your numbers won't match up nicely there. It doesn't really matter. So let's have a look at what those roots look like. Okay, so they are the points. That's when you plot the points. So that's your z1 through to z5. And then if we look at them with the line going from here, the line segments, we'll see this. So you can see that these roots are symmetric, in this case, about the origin, right? And that's what you should be looking for when you're dealing with one in the form of, say, z to the power of 7 equals 796. That's the first thing to notice. The next thing to notice here is that we had one which was z to the 5 is equal to 243. So my first root here had an angle of 0. If instead I had done z to the power is equal to -243, we don't ever want to work with r to the power of 5 is equal to a negative number. So the way that we deal with negative numbers is that we would go z to the 5 is equal to 243 times, so to make that negative, we need to have an angle of pi. So it would be 243 cis pi plus 2n pi, right? Similarly, if we had z to the power of 5 is equal to 243i, so we're starting up here, we would set the problem up as 243 cis pi on 2 plus 2n pi. So I'm hoping some of you are watching and processing this, because this is a really common source of mistakes. And if you look at a whole lot of past papers for NCEA level 3, I can think of a couple of examples where the kind of merit level question has had a negative number. And I don't write the papers, but I'm pretty sure that's because we want to test whether students have really understood how to go from here to here. So keep an eye on that. The last thing I want to show you, just because it looks cool, is that when you link it all up, you get this lovely symmetric shape. Now, if you're doing scholarship calculus at DubC, you'll see a couple of problems that have cool polygon shapes like this. And when you see them from now on, you should be thinking about solving to find the complex roots. Because if you're seeing symmetry of the roots, you can often, work backwards and attach that to something like what we've got today. The last one that I want to do quickly is just to do one where we are using special triangles. So the second question in here that I want you to try is the 6th roots of 1 plus 3i. I'm going to do that quickly now. Okay, so we start with z to the power of 6 is equal to r cis theta to the power of 6, but I need to figure out what is this complex number. So 1 plus root 3i is one with the special triangles, right? Very bad drawing, 1 and root 3. So the angle in here is 60 degrees or pi on 3, and the magnitude is 2. So it's going to be 2 cis of pi on 3 plus 2n pi. By de Moivre's theorem, we get r to the 6 times cis of 6 theta is equal to 2 cis of this. Right, so r to the power of 6 is equal to 2, r is equal to the 6th root of 2. And next, we're going to have 6 theta is equal to all of this. So 6 theta is pi on 3 plus 2n pi. Theta is equal to pi on 18 plus 2n pi on 6. Now, most of you probably see that and want to simplify that down to n pi over 3. And I've been hammering all year that we have to simplify fractions. But this is one of those times where it's actually easier to give it the same denominator as that 18 and make it pi on 18 plus 6 pi on 18 times n. And now we're good to go with finding the roots. Okay, so do a wee table. Here's your n. Let's see, what have I got? Right, I've got them here. I think it is worth doing it something like a table so you don't miss any out. So when n is 0, z1 is going to be this. The next one will be this. So when n is 1, you'll have 7 pi on 18. We've got room for one more before we have to go backwards. So here we're going to have 7. So 7 plus 6 is 13 pi on 18. If we did another 6, we'd be around to 19 pi on 18, which is over there. So instead I want to capture that one going backwards. So Z4 is where I've got n is equal to -1. Z4 will be the 6th root of 2 times cis of, so be careful here, it's 1 pi on 18 minus 6 pi on 18. So cis of -5 pi on 18. And then Z5 will be this, -11 pi on 18. And our last one, so this one here that I looked at, will be Z6 is equal to the 6th root of 2 cis -17 pi on 18. So there you go, 12.5 minutes of video. Sorry that was so long, but that lets you now go ahead and work through a bunch of the ones in 18.3. So I'll update the tracker sheet later on today, so it's Saturday, so that you can get going on those early. So questions that you should do, you should actually do quite a lot of these, guys. So they start getting difficult down at around question 14. I'll try and do most of them right through to there, but I'll put the ones I want done into the sheet. Thanks for watching, and let me know if you've got any questions on this.